My name is Greg Carlson. I'm the president of NYARM, and I welcome you. And without any further ado, I want to wish the brains and brawn behind NYARM, our distinguished executive director, Margie Russell.
Thank you. Thank you, Greg. Thank you.
Good morning, everyone. My name is Margie Russell, and I'm the Executive Director of NYARM. A little bit on how I recommend you use these meetings. Those of you who are here should be taking it back, in essence, to your management company, and when you have your monthly management meetings, you take one of the selections from a previous meeting, and that is your in-house education. So we want to complement your in-house education with what you do here. So our recommendation is that at least one or two people from every management company should be here. Bring all of the issues that your company has on the topic at the moment.
Okay, we're going to get right into the program. When we put Val Lair's name on the flyer saying that he was going to speak today, so many people said, I am coming because I must listen to Mr. Lair. So this crowd, we thank you for. We wouldn't have had this many people out here in the middle, at the end of July, if it weren't for you. So I'm going to let you, Mr. Lair, introduce your background, tell us a little bit about yourself, and then you can get right into the program. We do have copies of this to hand out afterwards. Okay, we do have copies. Herschel Weiss is the owner of Ashokan Water Services. He has one of the displays. He is the inquisitor for today. So any questions that you might not think of, he's going to ask on behalf of the audience, but we certainly hope that you will also have questions at the end of the program, and we have mics set up for that. So at this moment, Mr. Lair, I'm going to turn the program over to you. Here you have this. If you want the handheld and then to be out here, whatever works for you. All yours.
That's fine. Thank you very much, Margie. Actually, he's not the Inquisitor, he's the Grand Inquisitor. I have to watch out about that. Well, thanks very much for having me today. My name is Valentine Lair. I'm a consulting engineer with Lair Consultants International. We are mechanical electrical consultants. We've been in business since 1969 here in New York, and we have offices in London, in Munich, Dubai, and 2 offices in Australia at the moment. So we've done a lot of projects, a lot of high-rise projects, and a lot of residential projects. So I was invited to come today to talk about hot water. Actually, I got the invitation to come and give a technical discussion, and I happened to be talking at the time about a water problem, and someone said that would be a good thing to do. And the point of what I was talking about was the fact that, you know, there's lots of ways of doing an installation, but you really got to think about getting to the right size. And the right size is an important factor, and that's what we're going to talk about today. Now, I know Margie said that at the end of the discussion, you know, that we can have questions and answers and what have you, but I would like to offer that during the discussion, if there's a point that's of particular interest and you have a comment, an addition, a deletion, something to say, or just plain verbal abuse, that's okay. I handle verbal abuse real good, I guess maybe because that's where I get a lot of it, but in any event, as you're going along, if you see something, we can talk about it. And I thought that while the topic was right sizing for hot water heaters, and we're talking about domestic hot water heaters in this case, one of the issues that we really need to talk about is just the whole concept. And one of the great examples of right sizing is in air conditioning. And I thought I would start off with that. This thing is not going to work real well, so if I could have the handheld mic, because I notice every time I turn my head, my voice drops off, and I'd like to keep it constant.
No, that's right, and we are taping this for future classes. Okay. So we do want good recording.
Okay, air conditioning. Right sizing in air conditioning is really an important thing. So how many of you have been in a situation similar to this? You've got a contractor and you're looking to put an air conditioning unit in, and the air conditioning guys come up to you and said, listen, I did you a favor. At absolutely no extra cost, I increased the air conditioning capacity so you'll never have a problem cooling this place. I would be willing to bet the majority of the people in this room have experienced exactly that kind of offer in one shape, form, or another. And the question is then, is that a wonderful gift, or is it the root of all your future problems? Now, we're going to have to talk a little bit about air conditioning and some mathematical principles and what have you. I don't expect anybody here to get an engineering degree this afternoon, although if you can, congratulations. But what we're going to be doing is talking a little about what really makes some of these things work. And as you know, when you begin to figure out what size air conditioner you need, you have to do some calculations. I've got to tell you that there are at least 12 really good manual calculation procedures I know about. I know of at least 8 different commercial programs which will give you excellent calculations. And I know about 6 sophisticated spreadsheets that various people who put together, which are excellent because they take into account all of the factors in determining what the load is. Or I got so many people who have these great rules of thumb. How much is the air conditioning load in this space? Well, let me see. It's about 900 square feet, and we should use 450 square foot. This is a 2-ton job, and that's the extent of the calculation. Well, I got to tell you, that inevitably leads to problems, and it leads to big problems. Recently, someone I know very well, came to me and said, I want to do an air conditioning project, and I want to get a contractor. So I said, well, look, when you go out and get your proposals from the contractors, would you please do me a favor and ask each one of them to submit to you a little calculation in whatever form he did it to justify the proposal and the size of the air conditioning. And what was really interesting was that he insisted on this, and when the proposals came back, he had 5 proposals. 4 of them had no calculations, and every time it was asked, how did you determine the size of it, the answer came back, I've been in the business 30 years and I know what this building needs. That's not good enough. The guy who did have the calculations, he sent the calculations over to me. I took a look at them. I disagreed with 1 or 2 factors. We had a short discussion. The installation was done, and it is delightful. What happens in air conditioning if you make the decisions to go wrong? Well, the rule, the biggest tool that engineers use is this thing. This is called a psychometric chart. And this was developed by Willis Carrier at the dawn of air conditioning in the era between 1915 and 1922. And this particular device is a way of calculating the properties of air. So along this ordinate, you have the temperature that you'd measure on a thermometer. Like a thermometer outside today says we're going to hit 93 degrees, and 93 degrees is somewhere around here. This ordinate over here has the wet bulb degrees. And the wet bulb is the temperature you get if you take a thermometer and you make it real wet and you sling it around. And basically, if you draw a line up to find what the dry bulb temperature is and you match it with the wet bulb, you have a point like in here, and these radial lines are relative humidity. And this chart tells you exactly what happens in a space, in air, in an air conditioning system for any condition. So if you have this room, for example, early this morning before the air conditioning was on, the temperature in this room was significantly higher, and they had a certain amount of moisture in it, and that developed the relative humidity. And the relative humidity for that condition might have been over here. And as you cooled that air and moved in this direction, you didn't change the moisture content, you did change the temperature, but you see the relative humidity went way up. And so as you cool air, relative humidity goes up, and for a constant quantity of moisture in the air, the relative humidity goes down as the temperature goes up. It's a complicated relationship. But it importantly also defines what happens in an air conditioning system. How do you get the humidity out of the air with an air conditioning unit? Well, most of you have a pitcher on the table, and you'll notice the pitcher has condensation on the outside. And whenever the temperature of an outside surface, like on this glass I'm holding, is below the dew point, it squeezes moisture out of the air. The moisture you see here a few minutes ago before I filled that glass was moisture that was in the air. It's now on that, and we've squeezed it out. And that's very important because air conditioning is not only air cooling. It is also controlling the moisture. Because if you take a look at this chart, you'll see that there's another relationship that plays out. And that relationship is the relationship between relative humidity, temperature, and comfort. So this blue zone is generally the outer limits in which most people are comfortable. There are some people who are more comfortable in one zone or another, but that's the zone of comfort. And if the relative humidity goes over 70%, regardless of the temperature, you're uncomfortable. You may be cool, but the clamminess of the air makes you uncomfortable. And if the relative humidity drops below 30%, everything's too dry. Your nose and your lips and your mouth dries out. And more importantly, as you're walking along with your rubber soles shoes on this beautiful wool carpet and then go and touch some metal, of course, you generate a lightning bolt about 3 inches long. And that all has to do with operating in conditions that are outside these parameters. So it is important for you to lower the humidity as well as cool the temperature. And that's very interesting because now if you have a room and you have an oversized air conditioning unit, you turn the air conditioning unit on, the thermostat says it's too hot in here. The air conditioning unit goes on because it is such a huge capacity, it immediately and very quickly reduces the temperature and then shuts itself off. Well, the temperature's right, but why is it uncomfortable in here? And the reason for it is that that unit with all that capacity came on and went off so quickly that it had no opportunity to squeeze the moisture out to lower that relative humidity to a point where it's comfortable. And that is a huge problem. I have seen that as a problem in more buildings and more applications than you can believe. And not only, let's take a look at this, not only is that a problem in terms of comfort, but it is also a problem in terms of your cost, your energy, what you're using. So for example, I just want to look at two little sketches here. This is typically what happens in a room. This could be an office, it could be a hotel room, it could be an apartment. And you have an air conditioning unit. Maybe it's a fan coil that's tucked up in the corner. Maybe it's a packaged terminal air conditioning unit that's a through-the-wall unit over here. It could be a variety of different devices. It could be a vertical fan coil, an end fan coil. It could be a number of different devices. But essentially in this mode, what you see is that this unit is circulating air. It's taking air from the room and it's circulating it. And all it is doing is cooling that air. And as long as you have a cooling coil in here that's on, that has cold water in it, it's also squeezing the moisture out. And the same thing is true here. But there's a second side to all of this, and that's the ventilation. And you know, in order for us to survive in a space, there has to be enough oxygen in order for us to breathe. And more importantly, it also has to reduce the carbon dioxide that we exhale, because as the carbon dioxide levels go up, we tend to get lethargic. Now, it may be okay to be lethargic at work, but you don't necessarily want to be lethargic at home or at some other location. But if you take a look at this, you have to, in order to get ventilation, get fresh air into a space and also get rid of the exhaust, which moves the carbon dioxide out. Now, if you look at this, typically, if you have operable windows, for example, in residential units, the outside air comes in, and it also exhausts. For example, it exhausts through the toilet, and it supplies in through a living room or a bedroom window or what have you. But here's your air coming in. The package terminal units also have the ability to take air in through it, and sometimes you have a dedicated air supply. This is called a primary air supply, and it's very interesting, very usually found in hotels. And it's important because this air that comes in is not just plain fresh air, but it has been pre-dehumidified and preconditioned so that when the air comes in here, it is null air, or the air at the room condition, and therefore the actual room unit doesn't have to take that load. But as you can see over here, when you have an air conditioning unit like this, and you bring this air in, everything is good because that air goes through this coil. When it comes through the window, it doesn't. When the air is exhausted out over here, whatever air is exhausted out here is made up in here, or it's made up over in here. But the outside air is where all this bad moisture comes from. And so consequently, what you really want to do is you want to, again, make sure that these units see that moisture as quickly as possible. Because when that air comes in, you'll have an area where the humidity right around the air inlet point is high. And it's also uncomfortable. So, getting back to the psych chart, you can plot areas of comfort, and you can plot how long things have to run. And in a situation, by keeping the air capacity down, you literally are doing yourself a lot of favor. And this chart also speaks to that. If you take a look at a typical air conditioning unit and you say, oh, well, this thing has an EER of 7 or 8 or 9, it only has that EER if it is running for a long period of time. If this thing, air conditioning unit, comes on, stays on for 2 minutes, and cuts off, look what happens. If this is one unit, at a 2-minute run, it has an EER of less than half its design capacity. And so that coming on and going off winds up increasing your electrical consumption by an awful lot. And even more than that, when you start and stop motors so frequently, you burn them out. And so a unit operating with this short cycling can give you all sorts of problems, not the least of which is a very short life and an early replacement, and that's also more capital cost. So all of these things are very important. But more or less, if you go and you have a situation where your detailed calculations show that the capacity of a unit, or the actual design requirement is, let's say, 38,000 BTU. There's 12,000 BTU to a ton, so it's just a little over 3 tons. And you have the choice of buying a 3-ton unit or a 4-ton unit, don't hesitate to buy the smaller unit. Because even though it may not drop the temperature all the way down, it will run for such a long period of time that it will squeeze the moisture out, and with the lower humidity, you will be equally comfortable. So it's a cheaper unit, it uses less electricity, it performs better, and more importantly, it controls that humidity. And what's the problem with the humidity? Well, the biggest problem with the humidity, this is just another chart, by the way, that defines the fact that humidity is a big impact factor. At 50% relative humidity, it has no influence on your comfort. But as the humidity gets higher and higher, you see it very quickly gets to a point where it has major influence on how comfortable you are. So it's important for that point of view. But the chart I wanted to show you is this friendly chart. This is a laboratory chart, and what you're looking at here is mold and mildew that's grown. And this mold and mildew is very frequently in evidence in buildings that have high humidity levels, and high humidity levels come from oversized air conditioning. So for example, in here you can see this is an attic where you have big mold problems and mildew problems here. This is traditional on exterior walls where you have moisture penetration or open windows where there's a lot of humid air. You wind up getting mold and mildew in carpet. You can see it in the carpet here, behind the carpet, and what have you. About 4 years ago, one of our clients asked us to take a look at Gainesville, Florida. And we went down, and what happened was this classic example. There was a through-the-wall unit, and the chief engineer was told to buy some new units, and he looked at the capacity, and he went out and talked to a supplier. And for no extra cost, he got a bigger unit, and he put it in. Well, it did nothing to control the humidity. And when you walked into those rooms, they reeked of mold and mildew. And you saw evidence like this of mold and mildew everywhere. But, you know, it was like nothing I had ever seen. This thing was, it just reeked. And the mold and mildew, you look over here, you know, you smell it, but you don't smell it like this. So I had the opportunity to look at the room really closely. And at one point, I happened to get on my hands and knees on the carpet next to the bed, and I lifted up the, whatever they call that little drape thing that covers the base of the bed. And I looked underneath the bed. And what I saw was a field of mushrooms growing. There were actually mushrooms growing under the bed. And the housekeeping people, you know, they cleaned the place up, but they were not meticulous enough to move the bed to look for the mushrooms. Or on the other hand, maybe they were harvesting for them for some extra income, I don't know. But that's the kind of problem you can get. And it has everything to do with coming to the right size. So the next time anybody comes around and says, you know, I'm going to make you this offer, your answer is, thanks, I appreciate the offer, but please just right-size it. That's important. Now, the main part of the topic. Yeah, we'll try to do it this way. Maybe I'll hold on to my tie. Okay, what I really wanted to talk to you about is water heaters. That was the topic I was asked to talk to you about, and right-sizing of water heaters. And this is really a good topic. Now, as you know, water heaters come in lots of different sizes, shapes, and varieties of things. But so, for example, this is a storage water heater, direct-fired. You know, this is a steam-fired water heater. These are instantaneous water heaters. This is a gas-fired storage water heater. This is an oil-fired heater. You know, so you have all of these different types of water heaters. What we're going to be talking about today is water heaters, and it is the principle of water consumption and water heating. And so when we talk about this, we're talking about all types of water heaters. It doesn't make any difference whether your water heater is heated, your water is heated by steam, either your own generated steam or Con Ed, by gas, by oil, by electricity, by heat pump, by geothermal. Doesn't make any difference. It's really all the same thing. It's just different fuel sorts that we're talking about in here. And with these different types of water heaters, there are some very interesting things that happen. So let's begin the discussion a little bit by water usage. What you're looking at here is monthly water usage. And I imagine that nobody, including myself, can actually see what that chart says. So if you'll excuse me, we'll take the next one where I've sort of cleaned it up a little bit by putting some parameters on it. And this happens to be the water usage for residential for low-use homes. All right? And it's kind of interesting because what it shows you is a typical profile. Middle of the night, little or no water usage. All of a sudden, people get up. They're taking their morning showers, preparing breakfast, getting everything ready, washing the car, whatever. It drops off. There's sort of the middle of the day usage. This is something around lunchtime. It drops off after lunch, dinner preparation, and it goes down. This typical morning, noon, and evening peak shows up on any kind of residential chart of this nature. And you'll see one in here a little bit later, which we did on a research project which we did for some hotels. But again, you can see what happens over in here. And what you find here is that that is the peak time and the peak usage of water. So you have to be able to meet that peak. But obviously, the peak is significantly greater than the average. If you drew a line in here for average, it would probably be a line over around here. And if you did the calculation, you'd find that the peak usage is probably very close to 5 times the average usage. That's a residential number. It also happens to be a hotel number if you include the public areas, not if you include the, just the guest rooms. But that's the kind of thing that happens. And I want you to look at this thing, because when I started years ago studying these hot water curves, I was always fascinated by something. You see this number in here is around 1,100. That's 1,100 gallons on a monthly basis. And you'll notice that the peak is about 8 o'clock in the morning, and you notice that that's a low-use home. All right? Now, here's the same curve for a high-use home. Now, what happens is that this is, you know, more luxury housing, more upscale housing. And look what happens here. The middle of the day goes to just average. There's no lunchtime peak, because people in upper income categories don't eat lunch at home. And you would think that people who are wealthy are more leisurely and therefore get up later, but look where the peak is. It's at 6 in the morning. And look at the value of the peak. It happens to be 3,700 or 3,800. Compare that to the 1,100. They're using 3 times as much water at the peak. So you see, there is no stand at home. There's a wide variation. And if you have, for example, as many of the huge mixed-use buildings we're doing have some moderate income and some upper-end income housing, you can't use the same set of calculation figures, because not only does it give you the wrong solution in terms of the peaks, but it also avoids the center peak. So when you begin to think about delivering water, remember you've got to deliver the peak quantity, but at the end of the day, you've got to deliver all of the water that was used for the day. And we'll see that in, I hope, a clearer chart in a minute. Does anybody have any questions about this or any observations? I know there's a lot of people here who are in residential. Yes?
Wondering how the cold water factors in.
Say again?
How the overall use of water, cold water, does it get factored in on this?
Right now, this is only hot water we're dealing with. We're just limiting it to the hot water end of it now. I have lots of things. The cold water runs parallel to this, but it isn't quite the same, because this is just the hot water end of it. Okay? All right. Now, there is, you know, we've all heard of ASHRAE, American Society of Heating, Refrigerating, and Air Conditioning Engineers. ASHRAE has a technical committee 6.6 on hot water usage. I've sat on that committee for quite a number of years. And they have in the ASHRAE handbook over the years, you will have found lots of different ways of sizing hot water. Those different ways, more or less, are empirical. An empirical method is a method that has been calculated by just observing what works. It isn't the result of hard scientific calculation, but it is a mathematical expression of what's been observed. Well, again, the ASHRAE people have been looking at all of this as well. And if you look at the ASHRAE data, which is different than the data I gave before, you get these patterns. And this is rather strange, because this is the nationwide averages, and this is the high profile. Okay, you see, again, it misses that lunchtime. But look at the low profile. Low profile is about the third factors that we saw before. But the nationwide, somehow or other, the center part of it is also missing. But this is the data which ASHRAE supplies.
Is the low end where it's not at 0, is that just representing leaks?
You mean down over in here? No, because on a nationwide, there are a lot of, I mean, for example, if you go to Manhattan, and you do a hot water study, there are a lot of people who are up at night who can't sleep, take a shower, decide to make hot water, wash the dishes, and do things. There is usage. It doesn't ever really go to zero. It may in an individual residence, whether the residence is an apartment or a house, but if you have a conglomeration, someplace along the way, there's always somebody using hot water. Okay? All right, so we have all of this. Now, I want to show you another chart, which is this one. This is excerpted from a technical paper that I did for ASHRAE, and then it got published in a magazine, and this is hot water problems in hotels. And so what you're looking at here is an actual hotel, and this is the long-term peaks in the hotel. And you can see how exaggerated the morning and the evening peak are. And the difference, of course, in the hotel, and this happened to be a resort hotel, was that people at the end of the day want to take a shower and go out. So you have that higher peak at that point. But what's very interesting in all of this is as follows. Look at this chart up here. 0 to 10% of the flow. You are actually using water at 0 to 10% of the peak, that's the peak, 9 hours a day. And between 10 and 25% of the peak for 5.75 hours per day. Right? Between 25 and 38, 5 hours, 38 and 55, 4 hours. Between 55%, half the peak, and 83%, 15 minutes a day. Only 15 minutes a day. And the peak flow, between 83 and 100%, 5 minutes a day. So if you are designing for a peak condition, which you have to do, you have to meet it. You can't say, oops, sorry guy, you're over your limit. You know, what's it, you go on the computer and your bandwidth has been exceeded. You know, we can't do that. But we're designing for a condition that we need only a fraction of the day, a very small fraction, 5 minutes of the day. There are 1,440 minutes in a day. Well, that's a very telling kind of a situation, because it tells you that while you have to design for the peak, you really aren't there very much of the day. Okay? So keep that in mind. Keep that in mind, because next we'll look at this chart. Let me go back one more time. Just so I know what to say next. How many people here have taken calculus at all? It's a fair number of people. Okay. Well, you know, one of the things in calculus is integration, right? So an integration of a curve like this is actually determining the area of the curve. Now, I've blacked the curve out. Rather than having that as just a straight line, I've blacked it out because at any point in time, like this time, the area that is all in here represents the integral of that curve. Now, that's about as heavy as we're going to get in mathematics. But if you actually study that, what happens is the curve you looked at before, that curve we just looked at in the slide, can also be represented by this curve. This curve here, which doesn't look very useful, actually is exactly the same curve that we looked before, but shown in a different way. It is shown as the integral of the other curve. And what this thing does very simply says that if I had the first 5 minutes of the day from midnight till 5 after midnight at 1 gallon a minute, I start at 0 over here. At the end of 5 minutes, I will have used 5 gallons. And then if I go to the next 5 minute period of time and I know how much water rate was, I can compute exactly what the total water used was. This value over here is the total water used as a function of the day. And this is the tool which anybody who knows about water sizing finds most useful, because it enables you to convert a peak requirement into something with storage. And storage is a wonderful thing because instead of designing something that has all of the energy impact is big enough to meet that peak, which occurs for 5 minutes of the day, you can have a much more efficient, smaller device running for a longer period of time and storing water to enable you to overcome that peak. And that's the chart that does all of that. So let's, in that event then, take a look. There really are only two types of water heaters in a generic sense. The first of those are instantaneous water heaters. And they're also known as on-demand water heaters. And as you see, they can make hot water as fast as is required to meet the demand. They're usually electric or steam. They're small in size, and they have no storage. Now, we're looking at two images here. This upper image happens to be an Airco steam-fired instantaneous hot water heater. We'll take a look at what's inside of one of these things in a minute. And that's a steam valve. This other one is a little electric. In here it has a huge electric heating coil. And again, you can see there's no storage. This is just equipment. Now, going back to that chart where we saw the peak, this thing has got to be sized with energy coming in and with capacity and size so that it can make water instantaneously to meet that peak demand. So you can see it's a very big device. It has a lot of energy input, but it's used to its capacity 5 minutes a day. The rest of the time it isn't. So this is one type of heater, instantaneous water heater. All right, and if we take a look at this image, you can see the comparison. This is for a single house. This is what a storage hot water heater looks like in terms of size. And this little thing on the wall over here is the equivalent instantaneous hot water heater. Obviously, architects and people like to put these things in because, you know, they don't take very much room and they're not obtrusive. And, you know, this thing has gas that it burns, and it also has a flue, and this thing doesn't need a flue. So there's a lot of advantages to it. But this thing easily can use 4 or 5 or 6 kilowatts of electricity. Now, when I tell you that many homes operate their entire house, Long Island homes that were built in the 60s and 70s, you know, would operate very satisfactorily with 3 or 4 kilowatts peak demand. And here's a heater that uses the same capacity as a house. Why so much? Because it's got to make a lot of water for that peak. So that's what's happening over here. And if you begin to take a look, these are some pictures. That's that same hot water heater. What you've got on the inside is, you see, it's all coils. And basically that gives you heat transfer surface, and this is a steam control valve. And you literally blow steam into these coils, and the steam rate goes in at a very high capacity in order to hit peak demands. And this is a little bigger in the steam mode because it's intended for a multifamily residential unit, whereas something like this is for a 1 or 2 family home. And this is an electric model. But that's what the interior of these things tend to look like. All right? And if you then begin again to go back, and now I'm coming back off of the hotel thing, you can see what happens over here. Those instantaneous heaters, the capacity is this. And by comparison, if you went to a storage water heater, what happens is that you could figure out what the average you needed. Now, one of the interesting things about this, and again, this is an engineering thing, is that the slope of the curve here is equal to the value of that point. So on these things, when the usage is low, the slope is more flat, like over in here. When the usage is very high, the slope is much steeper. But if you were to connect that point by that point, that slope would be the average slope you needed for the day. And so if that peak capacity were 5 times the average, you could actually put in a heater that is 1/5 of this capacity, 20% of the capacity, 80% energy saving, let it run for the entire day, and you would have all the hot water you needed, except that you would be taking the hot water out of storage rather than making it instantaneously on demand. All right? So, I wanted to make one other point over here. That point is that you see over here in this chart, we are also tracking temperatures. This is from a technical article. You know, when you have a storage water heater, what are you storing? If I asked the question here, I would think that if I said, what am I storing in this hot water heater? It's sort of like, who's buried in Grant's tomb? Well, I'm storing hot water. Well, yes and no. We are storing hot water, but we're not really storing water. We're storing heat. And one of the things you can do if you run into trouble in your sizing or in your operations, and I keep running out of hot water, I got a hot water storage heater. I'm storing the water at 120 degrees and I run out of hot water. Well, okay. But you could, for example, store that water at a much higher temperature, like, for example, 180 degrees, and then as it leaves the heater, what you can do is blend in cold water to bring it down to your utilization temperature for distribution in the building. So there's always a way, within the context of these things, of fixing undercapacity, either by adding storage, by storing at a higher temperature. You know, there's always a way of fixing this in not too difficult way. So this just is from a couple of jobs that we had in the office. I just went looking around some drawings and I picked these up. But you see, here's one that has storage water heaters, and here what we're doing is we're storing the water a little bit on the hot side. And you see what we do. We generate the water hot, store it hot, and we amplify the capacity of this by blending in some cold water to some very hot water and then running it out to the system. These are also instantaneous heaters where we have an amplification, and what we're doing there is, again, we're using that mixing valve to control the temperature. And this is another storage water system, and again you can see that we've added the automatic mixing valve, and that's this device over here. Yes?
Please stand up and talk into the mic.
Yeah. Okay. The question is, if you heat the water to a higher degree level, then the recommendation is for the heater, it does give you hotter water. You can blend it, and it'll last longer. Does it deteriorate the unit itself? So its life would be shortened.
No, it doesn't, because the interior of those hot water heaters are designed to operate at temperatures up to 200 degrees with no penalty. So the answer is no. Now, there's a whole discussion we could have on hot water. I mean, everybody here, I'm sure, has heard about Legionnaire's disease and all of the evils that come with it. And there are some people who are suggesting we should really make the hot water very hot to ensure that we've killed off Legionella. There's a benefit to that. Other people claim that that's not necessary. But the hot water itself at a higher temperature will not cause any damage to the storage vessel. Those storage vessels are designed to operate at 200 degrees, and in some instances even above 200 degrees. Okay? Good question. Okay, now so let's look at the storage water heaters. And what we're looking at here, storage water heaters, you say have some different characteristics. They're direct fired, or they have an external heat source. External could be steam or geothermal or something of that nature. You have one or more storage vessels. It generally is gas, oil, steam, high temperature hot water, or electric, and it has a larger space requirement, mainly because you have to fit in the water that you're storing. So this is a residential unit. There's the hot water heater, and it heats the hot water, and it has a separate storage tank. And if you needed more storage, you could put a second tank in, or a bigger tank. This is a direct fired water heater. So this particular unit burns gas. It throws the hot gas through here, and all of the water is stored in here. This happens to be a steam-fired hot water heater. You can see the actual storage vessel, and this is the heat exchange mechanism inside, and steam would go in there. This can also be used with high-temperature hot water. All right? And again, some other types of arrangements. That's that unit. These are different arrangements. You notice here's another residential unit where the source of the hot water here is a coil in the boiler. And even large commercial installations often you have the heating boiler with a coil in it, and the hot water is made in the coil. And this is an arrangement like that. And this is a self-contained. This happens to be an oil-fired hot water heater, again. And it's also very interesting, you know, when people think about hot water heaters, it's amazing how many people I speak to, they begin to look at the hot water heater as a sort of a tank that fills up and unfills. For example, if you have a hot water heating unit, the makeup unit is good for, say, 20 gallons a minute, and your peak flow is 80 gallons a minute, what happens is that people conceive that you get 20 out of the boiler and then you get 60 that comes out of the storage tank. And the storage tank empties out and then later on gets refilled. That's not what happens, not at all what happens. And I thought this little chart is kind of interesting because what happens is inside of a storage tank, you have temperature stratification. The hottest water is always at the top. So you would fill this tank up with hot water when there's no demand. And then what happens is that as the demand comes on, water goes through the boiler. And the water that goes through the boiler should, for example, be heated up to 120 degrees. Well, it doesn't make it because the water, by virtue of the velocity, the speed at which the water is being used, is rushed through the boiler. So it doesn't get to 120. It gets to a temperature of under 120, and so it's cool and it comes in the bottom. And in essence, what happens is the water goes up and up like this, and we use the hot water off the top, and what we have in here is we have a thermal gradient, and eventually we run out of water. So when you look at the sizing of one of these heaters, if you haven't sized it properly, what happens is that a person taking a shower, for example, adjusts it for this temperature hot water. And then as the temperature gets cooler in this zone, you're standing in the shower, it gets cooler, what do? You go over and you throw a little more hot water in. And that means you're using the water here faster, and the water is going through here faster, and the temperature here is coming in cooler. So once you get to that point, the actions that people take to compensate for the water change drive you crazy. All right. So that is what happens in all of that. Now, what are the key points to remember? Well, as I say, you have to right-size things. In the, I don't know, I've been at this since 1962, so in the 45 years or so that I've been working on these things and designing, we've done hundreds of buildings, residential buildings, hotel buildings, and probably, I should say, thousands of buildings that utilize hot water systems. And what we have found is that whenever possible, utilize storage hot water heating. And going from the way buildings were built to the way buildings are built now, that sometimes presents a problem because lots of people these days are building condominiums where they want to have all of the utilities, including the hot water charge, on a tenant meter, and they'd love to have only one meter, and it's an electric meter. And so what happens is they want you to use electricity, and so you now can take a look at this huge storage system, which works very well, or you can look at an instantaneous system. And the instantaneous system is cheap for someone to buy and very expensive to operate later. So again, if your developer is pushing for that kind of a solution, you're sort of stuck with it. I can tell you also that there are a great number of unit owners who've come back to us and said, what can you do about the electric bills that I'm being imposed and all of the things that go with it? And what we've done very often is we've added a storage tank and converted this to a storage system, and the storage systems are always far more satisfactory. Buildings that have central hot water, going to storage is a no-brainer. It does not pay to skimp on the size of a storage tank. Again, there's a lot of objections. Gee, you're using up garage space that I could use for cars, or storage space, or, you know, I could rent out some additional space to a tenant, to a commercial tenant on the ground floor, but you got your water heater in there. The water heaters, if you put the right size storage in, never give you a problem and give you a great deal of flexibility. So we very much like that. Incidentally, in all of these discussions, we talked about what the peak usages are, but we have to understand that there is one special beast in residential structures which are a killer, and that's the jacuzzi. A jacuzzi can very often have 200-gallon capacity to fill. And of that, roughly 40% will be hot water. So you can go an 80-gallon load just on a single fill of a hot water tub. And that's brutal. And very often, in many of the instances we see again in luxury housing, is that the designer has done everything right and he's seen the bathtub and he's treated it as a bathtub, but if it's a jacuzzi, it's a killer. Okay? So what do we take away from all of this? If there's insufficient hot water, you can almost always store the water at a higher temperature and then blend it, or add more storage. So if you've got a system that isn't working quite properly, one of those two actions almost always will give you relief. All right? Storage reduces your utility demands, but does not reduce the total heating energy. If you're going to heat 100 gallons of water, the energy to heat 100 gallons of water is the same regardless of whether you heat it slowly and store it, or whether you put it through an instantaneous heater and have great demands. Instantaneous will require a much larger electrical service, and that will be not only in a particular unit, it'll be the cable leading to it, it will be the cables going down to the main feeder, it'll mean the service coming in from Con Ed. And so consequently, with those factors, I believe if you think about that and understand how these water heaters work, you have an idea of how you can get to right sizing. Okay? I'd like to, we've been going for just an hour. I was told to do this for about an hour. What I'd like to do is invite questions, comments, observations, and/or verbal abuse.
I got it. Hello. Val, you know, with the cost of energy being such that it's almost doubled in certain, you know, areas, and everything is either gas, electric, or, you know, steam, oil from steam, do you look at the source of the, you know, everybody's trying to be more efficient and trying to use less. Do you look at the source of the energy need when you're looking at if you're going to replace a hot water heater or something in that nature? Like gas would be better than a electrical hot water heater because your costs for doing that will be lower.
The answer is yes. I mean, it would be irresponsible for anybody who's for example, putting in a new hot water heater or changing out a hot water heater, not to look at what the relative costs of the various fuels are. Clearly, at this moment in time in New York, the cost of electricity is always the highest. But as you've seen, and I'm sure everybody has seen it, there has been this yo-yoing of is oil better or is gas better, and how it goes up and down. And you can make a choice predicated on what you know today and what you suppose will be happening, but that's always a bit of a guess. When we are really worried about that for large installations, we generally provide dual fuel burners. You can get a burner that'll burn gas sometimes or oil at another time, and that's a very positive thing to do. But from a larger viewpoint, let's be realistic in saying that we really are at a point where there's going to be a lot of changes made. And we all know, I mean, fact of life, there is no debate that we will at some point relatively now hit peak oil and gas production. And some people said it happened last October, some people say it won't happen until 2011, but at some point around now, we're going to hit the peak production, and it's all downhill from now. That's a fact. And what that means is that there is no question that oil and gas are going to go up further. And there is no question that an alternative fuel has to come online. I was asked to say a few words at lunchtime. If those of you who are around, I will in fact tell you some things that we've been doing a lot of study on, which I think will be very interesting. But I think what's happening is that we, in the next 30, 40, 50 years, will see a radically different energy picture in this country and around the world. And fortunately, you don't have to worry about that this week, because the life of a boiler, a hot water heater, is maybe 20 years, it's maybe 30 years, and the changes we're talking about are 30 years and beyond. So feel free to do a change to today's reality right now, but you have to think about what's going to be happening in the future. And the last part of that, I know you didn't ask this question, but I'm going to answer it anyhow. The last part of it is the best way to get your bang for the buck on hot water heaters is to really practice water conservation. Water is our next Achilles heel. And we are in what's known as the well-watered Northeast. Right. So we don't have a big problem compared to California and Arizona and Texas and the Midwest. We got lots of water, and yet we are running out of water. Today, the cost of water is phenomenal. When I started in this career, the water and sewage charges were 20 cents per 1,000 gallons. 20 cents per 1,000 gallons. That happens to be 15 cents per 100 cubic feet. So you know what the charge for 100 cubic feet is these days, or 1,000 cubic feet. But that was what water cost, and it is now close to 20 times as much, and the water bills will be going up again. Okay, any other questions?
Please go up to the mic.
Actually having the electric unit.
The mic, Mike.
What is the benefits of having the electric unit compared to the normal boiler that would run on gas or oil?
It's small. It doesn't need a fuel supply in terms of a liquid fuel or a gaseous fuel, so there's a safety factor that goes with it. It doesn't need a flue. That's the advantages of the electric instantaneous
As
heaters.
far as water conservation?
No, nothing at all. All that it's doing is heating the water you use. It isn't changing what you use. Water conservation is going in and limiting the flow, particularly in a shower head. Last week, as I mentioned before, we have 2 offices in Australia. We had the folks from our Brisbane office up, and we had them staying at one of the hotels in Midtown. I won't mention the hotel because I'm about to say something derogatory. They come from Brisbane. Brisbane has droughts. Brisbane has water conservation. They went and stayed at this hotel, and they said, they had a little placard on the dresser that said, "We practice water conservation." He said, "I must have had an 8-gallon-a-minute shower." He says, "Back in Brisbane, I get 1 gallon a minute, And if everybody frowns if you go someplace and you use the shower for more than 4 minutes.
Okay.
So that's what you got to do, and these things won't help you.
All right, now, back to the boilers. With the dual fuel boiler running on oil and gas, what additional type of infrastructure would be needed? Say I'm running on oil today and the price goes through the roof today, okay, it goes up $10 a barrel. And I wanted to switch over to natural gas because it's a lot cheaper. What additional steps or tasks would I have to take to suffice that?
Well, they're different manufacturers of dual fuel boilers, but essentially you have to have a dual fuel boiler, one which will burn either gas or oil. And then if you decide to make the switch, you go down, close a couple of valves, open a couple of valves, throw 2 control switches, and it may take you 8 minutes and you're one fuel to the other. That's all that's needed. The only thing you have to watch out for is a couple of peripheral things. I mean, obviously, there's a code provision that says that if you have 2 flues connected together, they can't have different fuels. So if you have, for example, an oil-fired device like your space heater and a dual fuel device like your water heater, they both have to be in gas or both have to be in electric, and the flue size has got to be sufficient so that you have sufficient flue capacity for either gas or oil, and there's a slightly different volumetric flow with those 2 fuels. Okay? Yes.
Obviously, you can also need a larger capacity gas.
Please, in the mic, please, Alan. Okay, we have a,
Well, let me ask this question, please.
Yes.
For a capital project, would you recommend installing a separate hot water heater so you can take your boilers offline in the summertime?
Yes, that is, if you're going to a new capital project and you have that choice, it's a much better thing to do because the boiler of the space heating boiler of necessity is much larger than your domestic water requirement. And so you've got this huge boiler idling along all summer long with all of the peripheral losses that come from the boiler being kept up to speed. I can tell you again, in my house, in every house that I have residential and I have some vacation stuff, but I have separate space heating and separate water heaters. I wouldn't have it any other way. The savings are significant.
Or approximately 100-family apartment, what would be your ROI?
Everything is different. I wouldn't want to answer that until they knew the facts and did the calculations. In the same way you do right sizing, you do sort of right answering. And you got to know the problem before you speculate too much.
Thank you.
Okay, but at one point or other, I would like to, if you have a chance, talk about return on investment, payback in years, and how you view an investment, because there's also a whole mathematical approach to looking at investments, and depending on how you look at it. In one instance, an investment may look, stupid. In another, it's dynamite. Same facts, just ways of looking at it. Okay? Yes, I'm sorry.
I just wanted to point out to the gentleman who asked about infrastructure that you're not going to be able to heat your water with your cooking gas supply. You're going to need a larger capacity gas supply if you switch over from oil to, for gas is cheaper now. That's the only point I want.
Yeah, absolutely. I mean, obviously, water heating is a load which is coincident with cooking. And so if you have a gas main that's in for cooking, it's sized for that. And if you're putting in another big load, you're going to have to increase the capacity to feed that. Yeah, that's a good point. Yes.
I wanted to ask about any additional energy costs of storing water at a higher temperature.
Well, there's always the possibility for thermal losses from the tank, but all of the hot water storage tanks that we put in today are well insulated. And yes, there is some loss that occurs from that, but it's not a significant amount if you have the tanks properly insulated. Yes.
Val, what about these newer equipment that have waste product like a Tico Chill or a Tico Cogen equipment that have hot water as a waste product? Could you use that as part of your plan, depending on the situation, of course?
The answer is yes. What you're talking about is some form of cogeneration. Cogeneration in the broad sense is that you are using energy for one property. There's waste energy as part of the process, and you divert that waste energy to something. And for example, in these mini turbines, as an example, you use the mini turbine to generate electricity, and you have a lot of hot gas that comes off. That hot gas is usable. It is usable in several of the pieces of equipment we looked at over here directly. Obviously, the one thing that is lost is that the waste heat that comes off of one of these processes has got to be used real time. And therefore, you've got to match load profiles against, for the two utilities. And just think about that for a minute. You use a mini turbine often at night when the loads are so low, you just go on mini turbine. And, you know, even though we didn't hit zero, the load is so low in hot water that unless you're being able to store all that hot water for later use, it doesn't make much sense. But cogeneration is used, I would say 35% of all of our projects today, the new buildings around the world, have some form of cogeneration in it. So yes, that is a use.
Yeah, the trend today seems to be towards shifting the energy load to the apartment, specifically by having heat pumps and such, thereby lessening the need for central HVAC. In general, this is a very general question, there's many factors, I'm sure. What is more efficient, central as opposed to decentralized HVAC?
Okay. When I go abroad, and we do work in lots of areas in the world, engineers are always talking about, I have the most efficient system. And it's always a central system. And I'll tell you why it's always a central system in a minute. And I look at this whole thing and said, yes, but that's not what the client wants. And you know, the argument then is, well, how can the client not want the most efficient system? And of course, the answer is the financial objectives of the client, the ownership structure of the building, the covenants dealing with common usages, what we call the condominium agreement here, what's called the body corporate in Australia, you know, different names in different locations. And in essence, what happens is they want to have as much on the individual owner's nickel so that they don't have to deal with common charges and approvals for common charges. And if you take the water heater and, in fact, the space heating and everything else, and you put it in the unit, and you just have an electrical meter, if it breaks down, it's their problem. You know, it's their problem, their cost, their problem, and nobody else has to worry about it, and it makes life easy. So there's a lot of benefits in terms of the practical day-to-day operation of a residential unit with some of the innovations you're talking about. But from a purely engineering point of view, what happens is that you are always better off at a central system. And let me give you just one example. Let's say you have 100 apartments, and let's say you know, each of those apartments has a 3-ton unit in it for air conditioning. Well, when you calculated the whole thing out, maybe the peak load was only 31,000 BTU, but you know, the size unit you used was 36,000, so you have a 3-ton unit. So you've got a little oversizing. And the difference is 5,000 BTU, and you did that for 100 units, it's 50,000 BTU, so you put more individual units in. But more importantly, not every apartment peaks at the same time, because you got a size for the peak, and that's when the sun is shining in the window, but the sun only shines in half the windows, half the apartments. The other side, it doesn't shine in. So there's a diversity factor. And when you calculate that all out, the central unit is significantly smaller. And it operates by virtue of being far closer to the actual right size at a longer runs, and therefore has more efficiency from that curve we saw. So the central unit invariably means always. Almost always, not always. There's always exceptions to the rule because every problem is a little different. But those units always tend to be more efficient. The issue has come that in the past, it was very difficult to measure how much cooling capacity apartments used when you had fan coils and 4 risers, and you had multiple taps. You couldn't get to a point where you could meter it. And as a result, it all became rent included, and that led to the arguments of, I never use my air conditioning, and he always keeps his place like a refrigerator, I'm paying for him. So to avoid all of that, we go to these other arrangements, but they are practical, social, and legal arrangements as opposed to efficiency issues. Okay? Yes?
Just one question. Say I'm the property owner of a large building, 400 or 500 units, was well designed with a large tank back in 1970. Since then, we've gone ahead and pushed water conservation, so now we have low-flow shower heads. We've reduced our water consumption tremendously. Should we be resizing that tank?
If the water level, if you have significantly more water storage than you need, the answer is yes, you should reduce it. And it comes back to the question the young lady over here asked is are there losses from tanks? And you're describing a tank that was 30 years old, and I presume it has 30-year-old insulation on it. And that insulation isn't the kind of super efficient insulation we use today, so there are radiation losses. And besides which, in New York City, regardless of what you're doing, 30 years is about the life of a tank, so you're going to have to replace it anyhow. So yes, make it smaller.
And the second question I think I have is the question that every manager faces. We always want to size everything correctly, and when we built the building, we had the ability to hire a large engineering firm to design it. But now when we've got a board saying, what should we do in this case, it becomes quite difficult to get an engineer to design the situation. We definitely can't get a Lear Associates to look at this little job. How does one practically go about retaining the right person who's going to design this correctly, and that the engineer is not just another guy who's going to do a rule of thumb and click out a number really quickly because cost is an issue at this point?
Okay, I thought this was one question. I thought I heard 4 questions.
Okay.
there. All right, but let me try to...
Well, I'll rephrase it. How does one go ahead and get the right type of engineer
Well,
for this job?
let me go. You made some points that I think are important. You know, we deal with condo boards, and I'm sure, you know, there are members here who are condo board members. But it is amazing how many experts are on condo boards. Just amazing. Who have the answer to everything and who question everything that's done. It's very difficult in that environment to actually come to something because there's a lot of politics, and condo boards tend to be political animals. Let me just leave it at that. Anyhow, the bottom end of the thing is that, to answer your question, number one, there are some really good equipment suppliers who know how to size things properly and who will work with you. Sometimes they charge a little bit, sometimes they don't if you buy their equipment, but there are some people who really know what they're doing. And going with those people is a solution. And there are a couple of engineers who do nothing more than do these small types of things, and they're very competent. If you talk to me, I might be able to give you a couple of names. But there are such people who do that sort of thing. You don't need to go into that. And it is possible to do it. And then I think the other point is that if you decide that you want to do this, and particularly in a condominium or cooperative board environment, there has to be a commitment to just simply do it and not have everybody second guess every issue and every statement. That's the way things get done.
Thank you.
We have one last question, Erwin.
I'll make it quick, Val. I love your presentation. I can't think of a thing to say to abuse you.
Thank you.
But I have a question. All right, we're talking about 100-unit buildings, 500-unit buildings. What about the small buildings that were built in the mid to late 70s and even as current as today? Developers are putting in individual hot water heaters in apartments. Would a building be better if that was changed to a central system, a single hot water system, or we would retrofit existing buildings? Are we more efficient with one or with individual units?
Individual units all have the advantage of being on 1 meter, but at the end of the day, I think you find that in even a small apartment, when we talk about small apartments, we're talking maybe 10 units, 18 units, something of that nature. you do have an advantage to having a central system. If it's properly sized, it will be smaller than the sum of the individuals, and it will be more efficient to operate. Okay. Thank you very much.
All right. Thank you. I think it was great. Thank you very much, Val.
Thank you, that was fabulous. Please make sure you sign in. Thank you.
A little bit on how I recommend you use these meetings. Those of you who are here should be taking it back, in essence, to your management company, and when you have your monthly management meetings, you take one of the selections from a previous meeting, and that is your in-house education. So we want to complement your in-house education with what you do here. So our recommendation is that at least one or two people from every management company should be here. Bring all of the issues that your company has on the topic at the moment